get started this morning. Welcome. Good morning. Let me start with a few announcements. One is to remind you that there is that CGH thing, the CGH Center for Global Health advising meeting about research internships. That's today, noon, here, pizza. Yes.
Also, this is hosting a personal training workshop
Tonight? Okay, that's in Quickswood Lab, for those of you who are in the 7 o'clock lab. But the CCE is your source for information for things like, you know, your CV, your resume, your personal statement, your info for research applications, those sort of things. Okay, CGH. Remember that problem set 1 is due on Sunday, this Sunday, at 11:30 p.m. at the desk. There's an envelope set up there for turning in your problem set, hard copy. The brain, I'm gonna postpone the brain dissection, the human brain, the craniotomy and the removal of the cadaver brain. It was scheduled for this Sunday, but I'm going to move it to next Sunday. It's optional, Sunday, it's optional. It will be around, I think it will be 2:30 on whatever a week from this Sunday is, next Sunday. The conflict is, on the one hand, we want to get the brain out as soon as possible and get it into fluid so that it firms up, so that we can work with it later in the semester. We want to do that as soon as possible, but on the other hand, I want you all to have the experience of working on the cadaver, you know, doing your first dissection, not on the brain. So, and only some of you, will, even in the Thursday lab, tonight's lab, will have had an opportunity to work on the body before Sunday, because next Tuesday is after next Sunday. So I'm going to wait, this Sunday. So bottom line, I'm waiting till next Sunday to do the brain. Okay? Schedule says it's this Sunday. That's not good. It's optional. Okay, remember that there is a lab tonight. The first lab is tonight, so if those of you who are in the Thursday lab, come to lab tonight, 7 o'clock, you have time, get ready to work on either the cadaver and the A&P review. I got an email from a student, from John Sacaleros, who signed up for the 7 o'clock shift, the Thursday 7 o'clock shift, but then remembered he made a mistake. He's got a conflict on Thursdays at 7 o'clock. Is there anyone in the 1 to 3 p.m. Tuesday shift who would be willing to switch with John? Nobody in the 1 to 3 o'clock shift can, has the possibility and ability to switch with John so that he can take the lab? Emily, you're willing to make that switch? Okay, thank you very much. Thank you very much. Okay. So, today we're going to be transitioning from review to, there'll be some review, but it'll be mostly new material, and we're going to be focusing on neurons. We're moving into neuroscience, cellular and molecular neuroscience. So, we're going to be talking about molecules. This is a crystal structure of a potassium channel. So here is the membrane. Here are alpha helices embedded in the membrane. This is the intracellular domain and extracellular loops. You did this in CellPhys. You did a poster about a protein structure. I guess all I want to say is that in this class we will not be getting into protein structure very much. You'll see a lot of those blob diagrams where a channel is just an oval in a membrane, the way I cartoon it on the wall. But it's your job to remember that that blob really looks more like this. It's a protein. It's got alpha helices, it's got beta sheets, it's got domains and subunits. We won't be going into it, but it's there in the background. Here is a piece of art by someone who is known as the father of neuroscience. Santiago Ramon y Cajal is considered the father of neuroscience because he, using microscopy and staining techniques, was able to identify the pathway of neuronal information, the pathway of information, making great inferences from just the way the cells were connected. So this is actually the retina, and we'll be talking about retinal photoreceptor cells and amacrine and horizontal cells and retinal ganglion cells that make axons that make the optic nerve. So we will be looking at networks of cells following in the footsteps of Santiago Ramon y Cajal. We'll also be talking about how the brain is incredibly highly connected. Remember, we've got 100 billion neurons in the brain. They're all connected. Each one of them is connected to maybe 1,000 other cells through axons and synaptic connections. So we've got 1 trillion synapses in our brain, something like that. So, we're going to be looking at 1 or 2 or 3 synapses at a time. So we're way orders of magnitude, 14 orders of magnitude away from the real connectivity. But of course, we can't talk about 1 trillion synapses. We don't even know how to look at 1 trillion synapses, but it's there in the background. And we will be looking at a human brain, right? But not this Sunday, next Sunday. There's a video that I like, and I would like to see if it plays here. This is my first time playing a video in this room with this connection. So it gets a little schlocky at the end. And it goes fast in some areas, right? So you can play this at home if you want. The URL is in the PowerPoint, which will be posted on Moodle momentarily, and you can go through it more slowly. So depending on your point of view, you can find this inspirational. That wow, I'm doing something that has been a true area of exploration for hundreds of years, thousands of years, and I'm now part of it. You're now part of it. So that's the way I approach it. You can also look at it and say, wow, that's a lot of stuff done by a lot of dead white men. Where do I fit into this? And it's true that, this, like many sciences, this field was, past tense, dominated by, cisgendered white men. But that's changing big time. The president of the Society for Neuroscience now is a woman. The person who made some of the most seminal advances in how glia work, the cells that myelinate, and the other major cell, the astrocytes, which are the other major cell in the brain, the person who really pushed that field forward, his name is now Ben Barres. Well, he passed away actually a couple years ago, tragically early from pancreatic cancer. His name was Ben Barres when he died, but when he was born, his parents gave him the name Barbara Barres because he was born a woman. So he raised the consciousness in the field of neuroscience and science in general about gender and transgender identity. And he wrote a book called before he died, when he knew he was dying, but before he died, he wrote a book called The Autobiography of a Transgender Scientist. And it's interesting from political, social, and scientific perspectives. As expected, he goes into his science in maybe more detail than the general audience can get. But you're not the general audience, or at least you won't be soon, and you'll be able to get a lot of what he's talking about. So it's a short book, and it's I actually have it in my office, but it will be in the Building Library. So. Okay, neuroscience. So what are our goals for today? Our goals for today are to review some anatomy, cellular anatomy and terminology, and then we will talk about equilibrium potentials. This is building on your knowledge from cell-phys, and an equation called the Nernst equation. And then we will use the Nernst equation to understand the resting membrane potential, remembering that nerve cells are negative at rest, and understand why they are negative at rest, and not just negative, but how negative, by using the Goldman-Hodgkin-Katz equation, understanding that, and in understanding that, get ready to work on some questions on problem set 1. I will introduce the simulator that you can use to solve problems using the Goldman-Hodgkin-Katz. In the old days, I gave people the same problems, but you had to calculate it using a calculator, and the logarithmic function. And it was painful, right? Because you got to plug in all those numbers into a calculator. Now there's a computer program that does it much easier, quicker, and allows you to focus your time on what does this mean, not plugging and chugging. And we will talk about depolarization and hyperpolarization, the language of electrophysiology. So here is I drew on the board last time the world's worst cartoon of a neuron. Here, this is an improved cartoon of a neuron, but it's a cartoon. But here are some of the words to learn about the cellular anatomy of a neuron. The cell body, the nucleus, dendrites, which are the connections to the cell body where receptors are located. And it's really, from a simple perspective that we will build on, it's the input area of the neuron, of this neuron. This neuron receives its inputs at dendrites and the cell body. Inputs at the dendrite and cell body. It also has outputs. The neuron has an input-output system. The output is the axon. It's got an initial part, also called the hillock. An axon that can be short, a millimeter, or can be long, several meters, depending on the cell. So this can be short or long, that's why it's broken here. And then the axon branches and forms terminal arborization. The word arbor means tree. And you can see this is the terminal arborization, branching and then making presynaptic terminals. And these terminals would then connect the next cell to the dendrites of the next cell in some network. So going back to Ramon y Call's picture, let's look at this red cell. It's a bipolar neuron. Dendrites, receiving synaptic input from these cells. Dendrites, cell body, nucleus, nucleolus, in the center of the nucleus, axon, terminal arborization, synaptic terminals, making synapses on the cell body of this neuron. This is also a cartoon, but not quite as simplified as this one. Here are some non-cartoons. So these are drawings of actual neurons. So this is more representative than even Cajal's drawing of what axons really look like in isolation. So these were cells that were filled with some marker and then microscopically drawn out, traced, to indicate all of the complexity of neurons. And so you can see here, dendrites, where there's the cell body, the soma. Here is the axon, and axon collaterals branching off of the axon. Of this is a pyramidal cell of the cortex. So you know we have a cortex in the brain. We'll talk some more about the anatomy of the brain later. Pyramidal cells have different names. This is a pyramidal cell, a pyramid cell. One of the most important types of cells in the brain. You may notice that there are these knobs or fuzziness on the dendrites. Those are called synaptic spines or dendritic spines. It actually Cajal gave them that name. In Spanish, he used the word espinas, which means thorn, because they were little. It looked like thorns on a rose bush to him under the microscope. So the Spanish word for thorn, espinas, became spines in English. Anyway, these little things projecting off of the neuron, off of the dendrite, are the spines where the terminal synapses are. That's where the synapses are, is on these spines of the dendrite. And you can see incredibly complicated dendritic fields on some cells. This is a cerebellar, so this is a Purkinje cell in the cerebellum, different part of the brain. I'm sort of throwing out the words there to start to use the language. We will, it's sort of the immersive approach to neuroanatomy. Okay, so here's a game. Those of you who have taken AMP1, no, this is AMP1. Those of you who have taken AMP2 know this game. Let's play this game for a moment. So the way we play this game is you pick a word here, and you tell me which knob it is. And you will tell me which knob it is because you will have the laser pointer. So you will have the laser pointer and you will say, Bob, I'd like to take axon collateral and put it here. Because this axon, this axon is branching off of this one, so this, I think this is the axon collateral. And I will then take the word axon collateral and put it on the knob that you indicate. And if it stays there, it's correct. And it's supposed to give me there it is. I don't know why it took so long, but it's supposed to give me the happy sound that it's correct. So, who would like to start? What we'll do is we'll just have a starting spot, and then we'll pass the laser around, and when the laser is in your hand, you choose a word, and you tell me which knob you would like to put it on, and then you pass the laser to the next person.
Okay, I'm gonna do myelin sheath.
Okay, myelin sheath.
So I just point.
Yeah, point to the button you want me to put it on.
Okay, I believe I'm getting.
Yeah, so some of these are complicated, and there could be wrong answers that are actually right, so we'll see. Let's just do it.
Is this correct?
Okay, let's try that one. Myelin sheath. It didn't like that one because, but that would be a correct answer. So let me show you what it wants to put on for the myelin sheath. I can't even remember. So this is not myelin sheath, but maybe this one is. Okay?
Well, we're just
So
trying to get.
yeah, that's why your answer was right, because it's just as good as that one. So pass the laser to somebody else, and we'll take another name. Dendrites. Where's dendrites? And which button? Which knob? Okay. Go ahead.
Nucleolus.
Nucleolus. And where do you want me to put it? Okay.
Who's going to be the first person?
I'm sorry, I couldn't hear you.
The axon,
Axon, and where do you want me to put it?
either this one going down or,
Yeah. Okay, so axon. You said either this one, that was one?
yeah,
I don't think it likes that one, because that's pointing to this arrow, and that's not the axon. So let's, and what was the other one you wanted me to?
that one or that one?
Yeah, I think that's the one it wants.
Especially one.
Oh, I would have chosen that one too. So let's see. Let's try this one here. That's your answer, not this one, but this one would have been correct too. Okay, pass it along. Let's just go sideways.
The direction would be the arrow.
The direction of signal transduction or transmission is which one?
The arrow.
Yeah, that's what that is pointing
I think I'm gonna do the axon.
to. Axon hillock. You want axon hillock or trigger zone? Which one do you want me to put it on? There's two that are very close. They're both equally correct. This one here?
Nope, nope.
This one here?
Nope.
No, it wants this one here. They're both, I mean, they're too close to be wrong, right? That's correct. What you said was correct. Claire? Nucleus? Okay. Okay. Terminal arborization. Okay. Pass it to, okay, go ahead and pass it to Mallory. Schwann cell. I would have thought that was correct too. Those are definitely Schwann cells, but I think it's pointing to this as the Schwann cell. So Schwann cells are the cells that make the myelin that wrap and insulate the axon. We'll talk about that some more. So Schwann cell is the name of the cell. Myelin is the material that wraps and makes the insulation. These things, so these are also Schwann cells, but from a physiological perspective, we call them internodes because of a name that isn't on the board yet, but you'll get to it soon. Soma. Okay, there's the soma, the cell body of this cartoon neuron. So dendrites, cell body, nucleus, axon. These are some of the key words. Jacob?
Do the initial segment.
Okay, so another name, right? So that's the initial segment, or the axon hillock, are the first part of the axon. The initial part of the axon.
I'll do the synaptic knobs.
Synaptic knobs are down here. I don't call them knobs, I call them presynaptic terminals, or synaptic terminals. And so here's the word that helps us define internodes. So Mackenzie, I'm going to have to give you your answer because there's only one choice left. The nodes of Ranvier. So the nodes are the part of the axon that is exposed between the Schwann cells that make the internodes. Nodes are where the axon of the neuron is exposed. Internodes are where myelin sheath from the Schwann cell wraps and insulates the axon. So you can play this game at home because you have the URL in the PowerPoint, but let's, we'll just move on. You get to choose what?
Oh, we'll just look at the website.
Yeah, okay. I mean, each time you load it, it'll be in a different order. So this is a way to learn the cellular anatomy of neurons. It's a game to play. So you can use the coloring book, you can use this tool, you can draw, there's a whole program that you can buy called Draw It to Know It. It's an anatomy program. So just, you know, and I think the concept, I haven't done it, but the concept is right. You draw out your own cartoon of a neuron and label it yourself, and then go back and check it against somebody else's cartoon of a neuron and see how it, you know, see if you got all the parts right. Draw it to know it. That's a way to learn. That's even more active than this game or the coloring book. So, let's talk about, so here's a cartoon showing the cell body, the dendrites where the receptors are, an axon projecting out towards us, with the axon being wrapped by myelin, forming this insulating layer, and the nodes of Ranvier between the myelin sheath that is created by the Schwann cell. So here is another cartoon of several axons from different neurons being wrapped by myelin from a single cell called an oligodendrocyte. Dim the lights a little bit so you can see this just a little better. I won't leave it off because I know you'll go to sleep. The oligodendrocyte is another kind of cell that creates myelin that wraps around the axon and insulates the axon. The difference, so what's the difference between a Schwann cell that makes myelin and an oligodendrocyte that makes myelin? Schwann cells are in the peripheral nervous system. So out here in the nerves in my arm, the axons are myelinated by Schwann cells. In my arms, in my face, in my leg. In the central nervous system, in the brain, or in the spinal cord, in the central nervous system, the axons are myelinated by oligodendrocytes. Two different names for related cells that are differentiated by where they are, either in the periphery or in the central nervous system. Here, the node is where the axon is exposed. So here is a electron micrograph of an axon cut in cross sections. The axon is projecting a mile that way and a mile that way on this scale. Here is the axon membrane. There are some things in there, some microtubules. And here are the layers of myelin wrapping around it, forming the insulating layer, insulating sheath. So here is a myelinated axon. Here's another myelinated axon that's off the picture. Here is an axon that is only slightly myelinated. So the degree of myelination, moderate, heavy, light, actually is different in different neurons. And that gives rise to different levels of insulation and different physiological properties of those axons. We won't get into too many of those details. Here is a fluorescence micrograph of an axon. So the axon probably, oops. The axon, here is the node of Ranvier. So the gray cloud is the myelin sheath. The green fluorescence is labeling voltage-gated sodium channels at the node of Ranvier. So here's the node between two Schwann cells. This is the axon. The axon sort of expands out this way and then goes here where we can't see it anymore. Voltage-gated sodium channels are highly expressed at the node of Ranvier, and voltage-gated potassium channels are expressed nearby in the paranodal region. And we'll talk about this is anatomy, the location of voltage-gated sodium channels and voltage-gated potassium channels, and we'll talk soon about the physiology of those channels. That's one of the goals for today. So let's talk about membrane potentials. Building on what we talked about in self-phys. We'll start with the level of material that you learned in self-phys and then build from there. So this is a simple setup. Here, the black dots are supposed to indicate molecules or atoms or ions, and in the case of electrophysiology, we're going to be focusing on ions. But this is just generic. This is supposed to be a membrane. On one side of the membrane, the ions have a high concentration, and on the other side of the membrane, the ions have a low concentration. We're just setting up the simplest system. You should be thinking, okay, what sets up that gradient? Oh yeah, for sodium ions, it would be the sodium-potassium ATPase that makes a high concentration of sodium on the outside and a low concentration of sodium on the inside. Or you should be thinking, okay, if I'm thinking about potassium, it would be the sodium-potassium ATPase that sets up a low concentration of potassium on the outside and a high concentration of potassium on the inside. So this is super generic, but you should be thinking, you should be applying what you know about ion gradients to make it less generic. The main point of this is that if there is a gradient, and if the membrane is semi-permeable, what's the word permeable mean? Permeation, permeability means something can go through it. This room is semi-permeable to human beings because there are a few places that human beings can go in or out of this room. It's not perfectly permeable because if I move in that direction, I will not get out of this room. That part of the room is not permeable. But that part of the room is permeable, and so this room is semi-permeable to us, to human beings. This membrane is semi-permeable. It allows this molecule to go through, but maybe not other molecules to go through. Okay? Somewhat permeable to the ion or to the solute that we're talking about. There is an equation that you don't have to know. do not have to know, but there's an equation that defines how fast ions or solutes flow. Flux is another fancy electrophysiological word for flow. Just translate flux into flow. Not pumping, flow, downhill flow, downhill flux. So if we have a gradient, there's going to be a flux of this, and we have a semi-permeable membrane that's permeable to this thing, then it's going to flow down its concentration gradient. And the flow is proportional to a constant and the concentration gradient, the change in concentration as a function of distance. It makes sense. It's proportional to the gradient and to some constant that is defined by the material moving in the fluid that it's in. And just to increase your level of inspiration, the scientists who solved the definition, and again, you don't have to know this, the scientists who solved the definition of this diffusion constant, how this molecule diffuses in this solution, which is proportional to temperature, inversely proportional to the viscosity of the fluid. If this fluid is honey, the things move through it much more slowly than if this fluid is water. The viscosity matters. Things move more slowly in blood than in extracellular fluid because blood is viscous. Okay, so viscosity matters. The size of the molecule matters. This equation is called the Stokes-Einstein equation, and the inspirational part is that you are now using material that Albert Einstein worked on before he solved the problems of general and special relativity. This is Albert Einstein. So big minds have been working on the things you're learning about right now. Diffusion. The equation that defines diffusion. So let's do what we did in cell phase, and then build on it. A cell with a high concentration of potassium on the inside and a low concentration of potassium on the outside because of the sodium-potassium ATPs. It's there, I'm just not showing it in order to keep this relatively. I'm going to put some rest, so here is a blob of a resting potassium channel. It's got alpha helices and beta sheets, and it's got structure, and it's got primary, secondary, tertiary, and quaternary structure, so you can imagine how complex it is, but I'm just going to draw it as this little donut. You imagine it's a donut, and we're seeing a donut in the cross section. It makes it makes this membrane now semi-permeable to potassium because it's a potassium selective channel. Well, which way does potassium flow? Down this, in this system. The pump has pumped potassium in, and now which way does potassium flow? Well, it flows down its concentration gradient from inside the cell to outside the cell. Okay? Diffusion. Also remember that there is no such thing as potassium gradient by itself. There are always counter ions, negative ions, that are present as well. So, and chloride is the most important counter ion. So I'm just going to draw chloride and chloride out here, and it doesn't matter that the marker is crummy because we're not going to be paying too much attention to it. But there are counter ions. But this membrane is not, let's say, very permeable to chloride, at least under these conditions. So chloride just stays where it's at. So every time a potassium ion moves out, it delivers a positive charge to the outside, and it leaves behind a negative charge. Right? One excess chloride ion. And potassium ion goes, and so let's now do it again. Another potassium ion moves out, leaving behind another negative ion, charge on the inside. and another potassium ion moves out, and another, leaving behind a net negative charge on the inside yet again. And I do this over and over and over again, and pretty soon the membrane becomes very negative on the inside relative to the outside. So, potassium diffuses down its concentration gradient and leaves behind a separation of charge. Negative on the inside, positive on the outside. And that separation of charge is a voltage, is a membrane potential. That's the definition of a membrane potential. Separation of charge in space. Negative on the, I guess, on the inside. Yes?
Is the ATPA still helping potassium?
The ATPase is maintaining the gradient, but the membrane potential is mostly due to this flow. Now, you could say, well, wait a second, this flow is going to dissipate the gradient. And the point is, it takes only a few ions to create this gradient. And we have a lot of ATPase, so the ATPase doesn't have much trouble keeping the gradient, even though we've got this flow going on. The ATPase can keep it up because it only takes about 100 ions to make the electrical gradient we're talking about, and the ATPase can pump 100 ions in a fraction of a second. So we're good. Now, will this continue infinitely? Will we get an infinitely large negative on the inside? No. This cartoon will eventually reach equilibrium. Equilibrium is reached when the concentration gradient, which is causing potassium to move out, is balanced by the voltage gradient. Remember, on the negative on the inside, cations like potassium are attracted to the negative charge on the inside. So the concentration gradient is a source of energy that moves potassium out, and the electrical gradient is a force of energy that moves potassium in. And when these forces, when this energy is equal to each other, when there's enough negativity on the inside to make the energy of the electrical gradient equal to the energy of the concentration gradient, we have reached equilibrium. And now there is no more flow. For every potassium ion that moves out due to the concentration gradient, there's a potassium ion that moves in due to the electrical gradient. Equilibrium. Aiden?
We'll just, never mind.
Okay, you can ask after break, or after class. We've reached a equilibrium condition. And this equilibrium condition is defined by an equation. It's the Nernst equation. So this is now a membrane that is permeable only to potassium. Let's see. We have a potassium gradient, and a voltage. The membrane is permeable only to potassium. Yes, we've got that. We've got a flow due to the concentration gradient. That was the equation that was on the board before. We've got a flow due to the voltage, which is another equation that you don't have to know. You do not have to know this equation. We have reached equilibrium. And now we can define the voltage of this equilibrium. And that is the Nernst equation for potassium. So let's walk through this for a moment. Because this is an equation you do have to use and understand. you will be using this equation or something like it in the homework problem. And on a test, I might ask you to use this equation to solve a problem. I will not ask you to do a calculation in a test. You will never need a calculator, but you will have to know, you might have to use this equation. So this, let's talk about, Alex,
Should we memorize it, or can we just like have it?
let's
on the
talk
test?
about what to memorize after I've walked through the equation. So this is the equilibrium, so every ion in the system that we're talking about has its own equilibrium. Potassium has its equilibrium condition, sodium has its equilibrium condition, chloride has its equilibrium condition, calcium has its equilibrium condition. Every ion has its own equilibrium. So every ion has its own equilibrium equation. Okay, so this is the equilibrium potential for a given ion is equal to some constants. Z is the charge of the ion. So for sodium and potassium, it's 1. For calcium, it's 2. Not a big deal. For chloride, it's -1. A constant times the natural logarithm of the concentration of potassium of the ion on the outside time divided by, so this is divided by the concentration of ion on the inside. So this is the ion gradient established by some pump. These two equations are exactly the same. This is one using the natural logarithm, and this is one using log base 10, and it doesn't matter. The only thing that changes when you go from the natural to the log base 10 is the constants on the outside of the equation. 8.
You know where they got the number 61 from?
By solving RT over ZF. By solving RT over F and using the difference between a natural logarithm and log base 10, that's where they got 61. It's using, the gas constant is R. I'm using some chemistry terms here that maybe, hopefully you've seen. R is the gas constant, T is the temperature in Kelvin, F is the Faraday constant. These are just chemical constants that can be numbers that can be plugged in, and if you plug them in together, you get 61.
That makes sense.
61 millivolts, actually, in the units. Because this is unitless, being a logarithm, and this has a unit, it's millivolts. This gives us an answer in millivolts. This is the equation that defines the voltage at this equilibrium condition. It defines how negative it is on the inside given this concentration gradient of potassium. This equation, if we plug in potassium instead of just ion, defines the equilibrium condition. Now, are we ever at equilibrium? No, we're never at equilibrium. If we're at equilibrium, we're dead. So, but before I do that, let me just convert the Nernst equation into English so that you can understand it maybe a little better than just the equation. Okay, I'm going to read these because, and then we'll take a break. The equilibrium potential for a specific ion is the voltage a membrane would have if it were permeable to that ion and only to that ion. If the membrane is permeable to one ion only, and we have a gradient, it will go to the equilibrium potential for that ion. At the equilibrium potential for a specific ion, that ion is at equilibrium. So the net flow, the flow down the concentration gradient minus the flow down due to the electrical gradient is 0. The net flow is 0 because it's at equilibrium. That ion is at equilibrium. None of the other ions are at equilibrium, but that ion is, if the membrane potential is at the equilibrium potential for that ion. If the membrane potential is above the equilibrium potential for that ion, and if there is some permeability to that ion, which there always is, the flow of the ion will be outward. So, if the membrane potential is more negative, below the equilibrium potential for an ion, the flow of that ion will be inward. So, let me just illustrate that, and we'll take a break. Equilibrium condition. No net flow of potassium. We're not worrying about sodium yet. Potassium is at equilibrium. No net flow. I do something to disturb this equilibrium. Let's say I introduce some positive ions to the inside. How could I do that? Well, let me add a little bit of sodium flowing in. But in any case, let's just, for this right now, if I make the inside less negative than it was before, the membrane potential is less negative. I just got rid of a negative charge. I'm making the membrane potential less negative, which is the same as above or positive. And now potassium can flow out down its concentration gradient, outward flow, because the inside is less negative than it was at equilibrium. If I make the membrane potential more negative somehow than it was at equilibrium, now there would be inflow of potassium because the electrical gradient is more than the concentration gradient. Okay? So that explains these last two sentences. If the membrane potential is above the equilibrium potential for that ion, there will be a inward, if the membrane potential is above, there will be an outward flow of that ion. And if the membrane potential is below the equilibrium potential for that ion, there will be an inward flow of that ion. That I just explained that was maybe clearer on the picture than it is in the words. But some people like words and some people like pictures, and that's why we're doing it. Let's take a break. We're going to then transition from equilibrium to real life, to a steady state resting membrane potential.